Right. So we were on Gauss's theorem. We discussed the equations for Gauss's law. We discussed Gauss's law in the last class. Today we'll see the applications of Gauss's law and questions based on it. Okay. So what is flux? What is meant by flux? Flux is the number of lines of force coming out of a surface or passing through a surface perpendicularly. Like we saw in the last class, if I take a surface like this, there are many lines of force. These are called electric lines of force. And these lines of force are resolved into two. Tangential component, normal component, tangential component, normal component. All these are resolved into tangential and normal components. And then the normal components are added up. Only the normal components are added up, the perpendicular components. We won't look at the tangential components. We'll have only normal components. And all those normal components are added. And that is called by the name flux. So flux is usually defined as, integral E dot ds. So let me repeat that one more time. What is electric flux? Similarly, there is magnetic flux as well. What is electric flux? We have a surface here. This is a surface, imaginary surface. And these are electric field lines penetrating the surface. And each field line is resolved into two components. Look at this. This is the surface, no? And the line is penetrating like this. It can be split up into normal component, tangential component. So every line is split up into normal and tangential components. And then all the normal components are added up. That is the physical meaning of flux. Flux is given by integral E dot ds. This is the mathematical formulation for flux. Okay. And second thing is Gauss's theorem. What is Gauss's theorem? If you got a charge here, and if there is a Gaussian surface around it, Gaussian surface is what? It's an imaginary surface enclosing a charge. Imaginary surface enclosing a charge. According to Gauss's theorem, the flux coming out of the Gaussian surface is 1 by epsilon 0 times the charge enclosed by the surface. So this is what Gauss's theorem says. According to Gauss's theorem, the flux means the lines of force coming out. All the lines are perpendicular, as you can see, right? The lines of force, the total number of lines of force coming out, flux, is equal to 1 by epsilon 0 into charge inside, charge enclosed by the surface. We did few questions as well in the last session, okay? Flux is 1 by epsilon 0 times charge enclosed by the surface. This is what we learned in the last class, and we did few questions as well. Flux linked with +1 coulomb, flux linked with a dipole. Do you remember this? Module number 2, ECF 02, paper, section B, based on flux and Gauss's theorem. Question number 4. Some of the questions are slightly advanced. Okay. A charge Q is distributed uniformly on a ring of radius R. A sphere of equal radius R is constructed with its center at the periphery of the ring as shown. Find the electric flux through the sphere. Read it again, you will understand it better. Right. A charge Q is distributed uniformly on a ring of radius R. A charge Q is distributed uniformly on this ring. Right. So we have a ring here. Ring has a radius of R. And then what? A sphere of equal radius R is constructed such that its center, with its center at the periphery of the ring. Its center should be where? Its center should be at the periphery. So I should draw the sphere like this. Look at that. So what have I? Oh, doesn't look good, right? So I have to draw an identical sphere. One is a ring, this is a ring, and I'll draw an identical sphere here. That also doesn't look good, right? So I have an identical sphere. See this? Oh, that looks pretty good, right? Okay, right. So what do we have now? We have a ring here. This is a ring. They have marked that in the figure. And the ring is what? Ring has a charge Q distributed uniformly over it. So it has charges all around, no? Plus Q, plus Q, plus Q, plus Q, or plus charges all around, or minus charges. Anyway, charges are distributed on the ring. And then what? A sphere of equal radius R is constructed with its center at the periphery of the ring. Center of the sphere is where? At the periphery or on the circumference of the ring. Am I correct? Center of the sphere is on the periphery of the ring. And see this? You know, this is center of this guy. So if I draw the radius, look at this. This is radius. Radius of ring or radius of sphere. Both are identical. And then what? I can complete a radius here. I can complete a radius here. So that this is what? This is an equilateral triangle because I've drawn a radius here, I've drawn a radius here, all sides are equal, which makes this angle what? This angle 60 degree. Similar way, if I draw one line here, this angle is also 60. Correct? So that makes it what? That makes it 120. 120. Okay, if this angle is 120, by the same logic, this is also 120. So how much of the ring is inside? How much of the ring is inside? Look at this. You know, I need to find, what is the question? Find the flux through the sphere. Flux through the sphere is what? 1 by epsilon 0 into Q enclosed. This is the equation for flux. Calculating flux, you can use this equation. For calculating flux, you can use this equation. 1 by epsilon 0 times charge enclosed. So that is 1 by epsilon 0 times how much of charge is enclosed by the sphere? So this is my Gaussian sphere, okay? How much of charge is enclosed? Look at this. So this is the part of the ring that is inside the sphere. I'm shading that part. I'm shading the part of the ring. Look at this. The ring was full. Actually, the ring was full, but only this much is inside. How much is this? I would say it is 1/3 of the ring. Why 1/3? Because this angle is 120. For 360, it is full circle. Since it is 120, this arc must be what? 1/3 of the ring. Total charge is Q. So for 1/3, the charge is Q by 3. So I can put it here, Q by 3. Answer is Q by 3 epsilon 0. I'm repeating one more time. Look at this. I know it's difficult, but don't worry. Right. So what do we have here? I'll explain the question one more time. This is a ring. The ring has charges all around. Okay. So plus, 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 plus everywhere. No, plus, plus. Right, like this. The ring has charges all around. But a part of the ring is inside. Part of the ring is inside. Inside what? Inside the sphere. Now this is my Gaussian sphere. Gaussian sphere. I need to apply Gauss theorem here. What is Gauss theorem? Flux. I need to calculate the flux coming out of it. Flux is 1 by epsilon 0 into Q enclosed. Outside region is not to be taken. Only the part of the ring which is inside the sphere is to be considered. How much is inside? How much is inside? I told you, if I draw a radius here, if I draw one radius here, if I draw another one, I'll get an equilateral triangle because all sides are equal. Similar way, if I draw one line here, radius, one radius here, this is also radius. So this angle is 60. So altogether, this is 120. So if this is 120, this angle is 120. Tell me what? This angle is 120. The arc against it is what? If you take a full circle, the angle is 360. Circle 360. And if I take an arc, which is making an angle of 120, this will be what? This will be 1/3 of the ring. 1/3 of the ring because 120, 120, 120. 120 into 3 is 360. So if it is 120, that is 1/3 of 360. 1/3 of 360. 1/3 of 360 means what? Charge also should be 1/3 of the charge. So 1 by 3 times Q. So that makes it Q by 3 epsilon 0. Did you understand? Question number 5. It's a textbook question. A point charge plus 10 microcoulomb is at a distance 5 centimeter directly above the center of a square of side 10 centimeter. So a point charge 10 microcoulomb. A point charge 10 microcoulomb is where? At a distance 5 centimeter directly above the center of a square. So we have a square here. See this? This is a square. Okay. And 5 centimeter above the square, you know, you have kept a charge plus Q, not plus Q, plus 10 microcoulomb, plus microcoulomb. The question is, what is the flux through the square? What is the flux through the square? So it looks like this. I'll tell you. Look at this. I have a square here. This is a square. And I'm keeping a charge here. Right. This is a square of side 10 centimeter. And 5 centimeter above, you are keeping a charge. And they are asking you to find the flux. How do you find the flux? So flux is coming like this, like this, like this, like this, like this. So you have to calculate the flux. I'll tell you how to do this. First of all, you have to imagine a Gaussian surface. This is the Gaussian surface. Gaussian surface. See this? Because I'll tell you the reason for it. I'll tell you the reason for it. So I have a Gaussian cube. I told you the most commonly used Gaussian surface is a Gaussian cube. Look at this. This is my plate. The bottom surface is my plate. Square plate, no? The question paper says that there is a square plate. the square plate, and right here we have a charge plus q, not q, plus 10 microcoulomb. Okay, so I need to find the flux through the bottom surface, but the problem is I can't insist that the flux is going through bottom alone. Flux can go where? Just imagine the room in which you're sitting now. Right at the center there is a charge. Okay, now will the flux go through the downward, bottom direction only, bottom plate only? No, flux can go to the left, flux can go to the right, flux can go in the forward direction, flux can go backward, flux can go up, flux can go down. Am I correct? Just imagine the room in which you're sitting. That is the Gaussian cube now. Okay, you are sitting in the middle of the room and you are the charge. Just imagine you are the charge. And where are the fluxes going? Where can the flux go? Flux can go to the right wall, flux can go to the left wall, flux can go to the roof, flux can go to the floor, flux can go to the front wall, flux can go to the wall behind you. Everywhere, no? Symmetry, uniformly. So flux goes up, flux comes down, flux goes to the right, flux goes to the left, flux goes into the wall, flux comes out of it. Right. So flux goes equally everywhere. Understood? Even though you're keeping it in the middle and there is only one plate here, the flux goes everywhere uniformly. Right. It has. This is why for symmetry we are considering a Gaussian cube. Now we can apply Gauss's theorem. What is Gauss's theorem? Flux is equal to 1 by epsilon 0 into q enclosed. So I'm writing it here, okay? Flux is equal to 1 by epsilon 0 into q enclosed is how much? Plus 10 microcoulomb. So this is actually what? Flux through 6 surfaces. How many surfaces do you have? The wall to the right, the wall to the left, the wall in front of you, the wall behind you, the roof, the floor. There are 6 surfaces altogether. Okay. So if there are 6 surfaces, one surface will get how much? 1/6 of it. I need to find what? Flux through the bottom surface only. This is actually what? I'll write one more time. This is actually what? Flux is 1 by epsilon 0 into q enclosed. So flux through one surface. My question is to find flux through one surface. Why? You know, in the question they say you have to calculate the flux through the bottom surface. So flux is going equally everywhere. That is evenly distributed. Right wall, left wall, roof, floor, front wall, back wall. All of the guys are getting equal amount of flux. So flux through one surface is what? 5 divided by 6. There are 6 surfaces. Okay, so what do we get then? You know, Q is what? 10 into 10 power minus 6 divided by 6 epsilon 0. 6 into epsilon 0 is 8.85 into 10 power minus 12. So 6 into 8.85 is 6 8s are 48, roughly 50. I take it as 50. Okay, so this is 10 into 10 power minus 6 by, this is multiplied 50 into 10 power minus 12. What do we get? 10 power minus 6 and 10 power minus 12 cut, 10 power minus 6. That goes numerator, 10 power 6. So 10 into 10 power 6 by 50, 0, 0 cut. 10 by 5 is 2. 2 into 10 power 5 Newton per Coulomb into meter square. That will be the flux through the bottom surface. Did you understand this? Question number 6. Again, a repeated foreign paper question. The uniformly charged conducting sphere, 2.4 meter diameter, has a surface charge density of 80 microcoulomb per meter square. Find the charge on the sphere. What is the total electric flux leaving the surface of the sphere? Okay, what is the question? A uniformly charged conducting sphere. This is uniformly charged conducting sphere of diameter 2.4. Diameter is 2.4 means what? Diameter is 2.4 means radius is 1.2 meters. Okay, what we need is not diameter. In fact, it is radius that we want. Right. A uniformly charged conducting sphere of diameter 2.4. Diameter is 2.4 means radius is half of it. It is 1.2. Has a surface charge density of 80 microcoulomb per meter square. 80 into 10 power minus 6 coulomb per meter square. Why 10 power minus 6? Because microcoulomb is mentioned there. This is surface charge density. Surface charge density is sigma, total charge by total area. Surface charge density is total charge by total area. Never ever forget it. Sigma is what? Sigma is what? If you remember, total charge by total surface area. Total charge by total surface area is called sigma. There are three terms: lambda, total charge by total length; sigma, total charge by total surface area; rho, total charge by total volume. This is for what? Linear charge distribution, like this. Charges are on a line. If the charges are on a line, like a string or something, you take a string, you take a thread and give charges to it. Charges are distributed on a line, and this is called a linear charge distribution. Lambda is called linear charge density, and it is Q divided by L. Similar way, if the charges are on a surface, as you can see, like a paper of your notebook, charges are on the surface. Their total charge by total surface area. That is called sigma, surface charge density. If we have a three-dimensional distribution, like the pen or something, right, like this pen, okay, it's a three-dimensional body. Charges can be even inside the volume. So there you have volume charge distribution, So you have charge per unit volume. Okay, so this is linear charge density. I'm repeating one more time. Charge distributions are of three types. Charge distributions. Charges can be distributed in three different ways. First one, linear charge distribution. Charges are on a line. Linear charge distribution. For example, you take a thread, you take a string, and then give charges to it. Look at this, charges are on a line. There you will find the total charge by total length. That will be called lambda, linear charge density. Right. Second one, you take a paper, you take a sheet, that is a surface distribution, area distribution. Charges are over an area. There you will find total charge by total area. That will be called sigma, surface charge distribution. And then what? Three-dimensional distribution. Three-dimensional distribution of charges. Charges are going even inside. Such a case, it is three-dimensional. So charge by volume. Charge by volume is rho. Rho is charge density, volume charge density. So this is linear charge density. This is surface charge density. This is volume charge density. In case you don't know, you can write this down. Okay, this is linear charge distribution. This is linear charge density. This is surface charge distribution. This is surface charge density. This is volume charge distribution. So we have volume charge density. Okay, hope you understood this. Anyway, we are looking at surface charge density. So the question is what? Question number 1, find the charge on the sphere. Easy question. Sigma is given. Sigma is 80 into 10 power minus 6. Okay, sigma, surface charge density is given. It is actually charge per area. Charge per area is 80 into 10 power minus 6. Cross multiply. Q will be 80 into 10 power minus 6 into 4 pi r square. Why? This S goes there. Area goes there. Area is what? 4 pi r square. For a sphere, area is 4 pi r square. So let us put the value 80 into 10 power minus 6 into 4 pi into 1.2 into 1.2. Radius is 1.2. Multiply, you get what? 80. 1.2 into 1.2 is 1.44. 1.2 into 1.2 is 1.44. 1.44 into 4 is 5.6. 1.44 into, this is 1.2 into 1.2 is 1.44. Into 4 is 5.7 or something. Into 3.14. Roughly 18. That will be 18. If you multiply 18 into 80 is 1440 into 10 power minus 6. So I can simplify if you want. 1, 2, 3 place down. It is 1.44 into 10 power minus 3 coulomb. That will be the charge. Okay. I'm repeating one more time. Question. We have a sphere here, no? Charged sphere, uniformly charged sphere. And they are asking you to find the total charge here. What is surface charge density? They have given surface charge density sigma 80 into 10 power minus 6. The sigma is what? Sigma, I told you, it is total charge by area, Q by S. So Q by S is this much. So Q will be cross multiply 80 into 10 power minus 6. 80 into 10 power minus 6 into 4 pi r square. That is 80 into 10 power minus 6 into 4 pi into r square. Radius is what? 1.2. 1.2 into 1.2. So this is what, if you multiply it yourself. 1.2 into 1.2, 1.44. 1.44 into 4, 5.7 or something, into 3.14. 5.7 is made 6. 3.14 is made 3. 6 into 3 is 18. 18 into 8, 144, 0. 144, 0 into 10 power minus 6. 1, 2, 3 place down, 1.44 into 10 power minus 3. That is part 1. Part 1. Part 2, they are asking you to find the flux. Flux is easy to find out. 1 by epsilon 0 into Q enclosed. So 1 by epsilon 0. Epsilon 0 is how much? 8.85 into 10 power minus 12 into Q is how much? Q is there in the question. 1.44 into 10 power minus 3. So if you cut 1.44 and 8.85, roughly 6. So 1 by 6 into 10 power minus 3 on numerator, 10 power minus 12 on denominator, 10 power minus 9 on denominator, that will go to numerator, 10 power 9 Newton per Coulomb into meter square. That will be the final answer. So you may have confusion with this calculation here. Don't worry. 1 by epsilon 0. Epsilon 0 is 8.85 into 10 power minus 12 into Q. Q I have found here 1 by 1.44 into 10 power minus 3. 1.4 and 8.85 roughly 6. You check it out. 14 sixes are 84. So it's very close. 14 sixes are 14 into 6 is 84. This looks like 14. This looks like 84 something. Okay. Anyway, when you multiply, it's roughly 6. 1 by 6 into 10 power minus 3 on numerator, 10 power minus 12 on denominator. So 10 power minus 9 on denominator. Take it over to numerator, 10 power 9. Did you understand this? Moving on to question number 7. Again, a repeated one. A sphere S1 of radius R1 encloses a charge Q. If there is another concentric sphere S2 of radius R2 and there be no additional charges between S1 and S2, find the ratio of electric fluxes through S1 and S2. In fact, we did this question in the last class. But anyway, I'm doing it again. A sphere S1 of radius R1. A sphere S1. This is sphere S1 of radius R1 encloses a charge Q. Encloses a charge Q. Okay. If there is another concentric sphere S2 of radius R2. There is a bigger circle, bigger sphere S2 of radius R2. And there be no additional charges between S1 and S2. Between S1 and S2, there is no additional charge. So there is only one charge common to both the guys. It is Q. They are asking what? Find the ratio of fluxes through S1 and S2. Easy question. 5. Flux through the first surface is what? 1 by epsilon 0 into Q. Enclosed charge is Q. Flux through the second surface is what? 1 by epsilon 0 into Q, because that also encloses same charge. So that will be what? Phi 1 to phi 2 ratio is to be calculated. 1 by epsilon 0 into Q by 1 by epsilon 0 into Q. They are getting cut. You are left with 1:1 here. The ratio is 1:1. Repeating one more time. There are two spheres. Read it again. A sphere S1 of radius R1 encloses a charge Q. Okay. If there is another concentric sphere S2, there is another concentric sphere S2 of radius R2, and there be no additional charges between S1 and S2. There is no additional charge in this space. In this space, there is no additional charge. Then ratio of fluxes. Fluxes given by 1 by epsilon 0 into Q. For the inner sphere, 1 by epsilon 0 into Q, because the charge inside is Q. And phi 2, 1 by epsilon 0 into, again the charge inside is Q. There is only one charge. So 1 by epsilon 0 into Q by 1 by epsilon 0 into Q, the ratio is 1:1. But there was one question once, they would introduce one more charge here. Then things will be different. Okay. In first case, you write 1 by epsilon 0 into Q. But in second case, you should write what? The outer sphere encloses how many charges? Q and Q. There are two charges. So you have to write 2Q. We did this question in the last class. Yeah, that's right. Next one, question number 8. It's a textbook example question. Previous foreign paper question. The electric field components are Ex is equal to alpha x raised to half. Ex is equal to alpha x raised to half. Ey is equal to 0. Ez is equal to 0, if I remember correctly. Let's read it. The electric field components are Ex is equal to alpha x raised to half. Ey is equal to 0. Ez is equal to 0, in which alpha is equal to 800 Newton per Coulomb into meter square, alpha. Okay. So what do you understand from this? Ex, electric field component along x-axis is alpha x raised to half. Electric field component along y-axis is 0. Electric field component along z-axis is 0. That means Electric field exists only in x direction. Electric field in y direction is what? 0. Electric field in z direction is what? 0. Understood? It's a typical question, which means this question will be asked in this particular way only. Understood? It's a typical standard question. Alpha x raised to half. Electric field exists only in x direction. Let's go on reading. Calculate the flux through the cube, the charge within the cube. There are two questions. Calculate the flux through the cube, charge within the cube. Assume that one side is 0.1. One side is 0.1 meter. Cube side is 0.1 meter. I'll draw the figure first, then I'll do. Look at this. Look at what I'm doing here. Okay, I have x-axis, y-axis, z-axis. Okay, I'm keeping a cube here, right here. This is my cube. Okay, I have a cube here. See this. Right, I have a cube situated here. All right. And what are the sides? This distance is given, it is one side 0.1. This distance is also 0.1. Okay, 0.1. So this distance is 0.1. They say it is A, but A is 0.1. So this is also 0.1. All right. So tell me about a cube. What do you think about a cube? I have a cube here. Just give me 1 second. Let me see if I can get one. Right. Okay. Just give me 1 second. Okay, this is not a cube. This is actually a cuboid. But for the moment, take this as a cube. Okay. So I'm keeping the cube here. All right. Just imagine it's a cube. How many surfaces does it have? 6 surfaces, right? Top surface, bottom surface, front surface, back surface, left surface, right surface. So every cube will have 6 surfaces. Am I correct? And what is the flux through the top surface? Look at this. This is area vector, no? Perpendicular. Where is the field going? I had told in the beginning that field exists only in x direction. Okay. This is how the electric field is passing. Electric field is existing. Electric field exists only in x direction. See this. Electric field is going in this direction and area vector is in this direction. So what is theta? 90 degree. Flux will be E ds cos 90, 0. Flux through the top surface is 0. Correct. Same way, flux through the front surface is what? 0, because area vector is towards you, field is going in this direction, angle is 90. Same way here, flux through the bottom surface is 0. Flux through the back surface is also 0. I'll tell you one more time. Look at this. There are 4 surfaces. If I take the top surface, this is how the area vector is drawn. Area vector is perpendicular. And electric field is going to the right. Angle is 90. Flux is E ds cos 90, 0. For the same reason, flux through the bottom surface, area vector is downward. There also flux is 0. Flux through the front surface, 0. Flux through the back surface, 0. For all these cases, theta is 90. See this. This is area vector. Field is in this direction. Field is always in this direction. Okay. This is area vector. What is angle there? 90 degree. Area vector. What is angle there? Again 90 degree. What is area vector? Angle 90 degree. What is here? Back side 90 degree. So flux through top surface, front surface, bottom surface, back surface will be equal to 0. Flux passes through the left surface and right surface only. Flux passes through left surface and right surface only. Just imagine a river is flowing. Will water flow up? No. Will water flow down? No. Will water come to us? No. Will water go into the boat? No. Water is flowing along x-axis. That's it. So it is cutting which all surfaces? Left surface and right surface. That's it. I can find the fluxes now. What is the flux through the left surface? I am doing it here. Okay. I am doing it here. Flux through the left surface. So if I take the left surface, flux through the left surface is equal to E into A into cos 180. Why is it 180? Cos 180? Tell me why it is 180. Because electric field is going to the right. For the left surface, the area vector is to the left. Area vector is to the left, as you can see. Look at this. When I consider the left surface, area vector is to the left, while the electric field is to the right. Angle is 180. So let us put the value. That is E. E into A into cos 180. Cos 180 is minus 1. That is minus E into A. That is minus E is what? E is written there. Alpha x raised to half into A. Minus alpha is written there. It is 800. into x raised to half. X is what? X is the location of the first plate. X is the location of the first plate. Where is the first plate? First plate is at a distance of 0.1. So 0.1 raised to half into area. Area is 0.1 square. I'm repeating one more time. Don't worry. Right. Look at this. What are we looking at now? We have a cube here, and how many surfaces? 6 surfaces. Top surface doesn't have flux. Bottom surface doesn't have flux. Flux doesn't pass through the front surface. Flux doesn't pass through the back surface either. Flux passes through only 2 surfaces, left surface and right surface. I'm going to find the fluxes through them. What is the flux through the left surface? Flux is given by E dot ds or E dot area. E A cos theta. What about theta here? For this surface, area is to the left, as you can see, and electric field is to the right. They are in opposite directions. Angle is 180, cos 180. Cos 180 is what? Minus 1. So minus 1 into EA, minus EA. So I'm putting the value here. What is E? Electric field is written there, alpha x raised to half minus alpha x raised to half into area A. That is minus alpha value is how much? 800. Alpha value is 800. X value, what is x? X means the location of the first surface. Where is the first surface? They say that this distance is 0.1. So 0.1 raised to half into area is what? Area of the square plate. Area of the square plate is side into side. That is 0.1 into 0.1. That is 0.1 square. 0.1 square. Okay, 0.1 square. So let us simplify this. This is minus 800 into 0.1 square, 0.01 into. How do you take the root of 0.1? This is 0.1 raised to half. 0.1 raised to half. How do we take it? If you don't use calculator, I'll tell you an easy technique. Okay, I'll tell you an easy technique. You have to write it as 10 into 10 raised to minus 2 raised to half. 0.1 raised to half is not easy to find out. So there is a technique. You write it as 10 into 10 power minus 2. It is still what? 1 place, 2 place. It is 0.1 itself. 10 into 10 raised to minus 2 raised to half. What is this? Then raised to half means square root. Square root. 10 square root is roughly 3.14. Why? Pi square is equal to 10 almost. Have you heard about it? Not yet? Anyway, just see this. Whenever you see 10, the square root of 10 is roughly pi, 3.14. Into what is square root of this? 10 power minus 2, 10 power minus 1. I can put it here. 0.314. When you multiply, this is minus 2 places gone with 2 zeros. You get what? 8 into 0.314. 8 into 0.314. I'll calculate 8 into 0.314. Rough value. 8 into 0.314. 8 into 0.314 is 2.5. 2.512 Newton per Coulomb into meter square. This flux is negative. Why? Because field is towards right. I'm looking at left surface. Did you understand this much? Having calculated flux on the left surface, you can calculate the flux on the right surface. What is flux on the right surface? I'm going to do the same thing. Flux on the right surface is, look at this. You know, E into A into cos of 0. Why 0? Because right surface area vector is to the right. Area vector is to the right. Electric field is also to the right. Theta is what then? 0. That makes it E into A. Because cos 0 is 1. Cos 0 is 1. E into A. That is equal to, E is what? Alpha x raised to half. Just like you wrote here, alpha x raised to half into A. Let us put the values here. Be very careful. Alpha is 800. X is what? X is location of right surface. Location of right surface. Where is right surface? Not at 0.1 like in the first case. Right surface is where? This much is 0.1. This much is 0.1. Together it is 0.2. 0.2 raised to half. I'll tell you one more time. Look at this. I put the value of alpha, that is 800, and x. Remember, first surface was where? First surface was at 0.1. But second surface is where? 0.1 plus 0.1. Look at this. This distance is 0.1. So it is at 0.2. 0.1 plus 0.1 is 0.2 raised to half. Area is what? Area of square. That is again 0.1 square. So let us simplify. That is 800 into 0.1 square. 0.01 into 0.2 raised to half. I have to find 0.2 raised to half. I am finding it here, 0.2 raised to half. It is better written as 20 into 10 power minus 2 raised to half, like I did here. Okay, like I did here. 20 square root is 4.4, roughly 4.4. You can calculate it yourself. Okay, if you use calculator, into 10 power minus 1. I'm taking rough value. One place down it is 0.44. So 0.44. This is what? These zeros with 0.01. 8 into 0.44. Let me multiply. 1 second. Just give me 1 second. 8 into 0.44. It's 3.52. It is 3.52 Newton per Coulomb into meter square. This is plus. That is flux on the right side. They are asking you to find phi net. What is phi net flux? Net flux is minus 2.512 plus. This is 3.52. I did a lot of approximations, so this is not as precise as the textbook calculations. There will be slight differences, but don't worry. Anyway, I'm just finding 3.52 minus 2.512, 1.008. I get 1.008 Newton per Coulomb into meter square. That will be the flux through it. Flux. In textbook, they got it as 1.05 or something. I don't remember. Did you understand this? So there is a second part of this question. You have to calculate the charge enclosed in the cube. Charge enclosed in the cube. You can use Gauss's theorem. When you say charge enclosed, when you hear charge enclosed, what should come to your mind? Gauss's theorem, charge enclosed. So flux is equal to 1 by epsilon 0 into charge enclosed. They are asking you to find charge enclosed. How do you take it? Cross multiply 5 times epsilon 0. 5 times epsilon 0. Phi is what? You got the phi value here. 1.008 into epsilon 0 is what? 8.85 into 10 power minus 12. 8.85 to 10 power minus 12. When you multiply this into this, 8.85 into 1 point something, slightly greater than 1. So it's roughly 9 into 10 power minus 2 Coulomb. That will be the final answer. Okay, let me put it one more time. You know, what is the next question? Second part of the question is to find out the charge enclosed within the cube. Within the cube, how much of charge is there? How do you calculate the charge? You can, charge enclosed is always given by Gauss's theorem. Gauss's theorem says that flux is equal to 1 by epsilon 0 into Q. So Q enclosed is what? Cross multiply 5 times epsilon 0. That is 1.008. 5 we have calculated here. Epsilon 0 value is 8.85 into 10 power minus 12. When you multiply this, 8.85 into 1 is 8.85. But this is slightly greater than 1. So answer is slightly greater than this, 9 into 10 power minus 12 Coulomb. Did you understand? Everybody finish this? There are some applications of Gauss's theorem. For the moment, I'll give you the equations. The derivation part we'll come back and do later. Gauss's theorem applications. What is the electric field due to a linear charge distribution? Do you remember? This is called a linear charge distribution. Right here, at a distance r, the electric field intensity is given by lambda by 2 pi epsilon 0 r. Do you remember? Lambda by 2 pi epsilon 0 r. Electric field due to a line of charges. This is called linear charge distribution. Actually, it is an infinitely long wire. Infinitely long wire. You draw a cylinder around this. You draw a cylinder and then you calculate the electric field, if you remember. Electric field at a distance r is given by lambda over 2 pi epsilon 0 r. But for calculations, never use this equation. Instead, you multiply with the 2. You make it 2 lambda. When you multiply with the 2, you can multiply denominator also with the 2. 4 pi epsilon 0 r. Why did I do this? Because 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. Otherwise, you'll have to substitute here. But this way, it's much easier, okay? Because there is a textbook question based on this. That's a direct one. They have given this E value, R value. They are asking you to find out lambda value. Okay, there is a textbook question. Repeating one more time. These are applications of Gauss's theorem. There are some applications of Gauss's theorem, one of which is removed from the syllabus this year. This is linear charge distribution. Linear charge distribution means what? You take a string and then give charges to it. There are lots of charges on it. And then you draw an imaginary Gaussian surface. This is a Gaussian surface, correct? Gaussian surface, Gaussian cylinder. Hope you remember Gaussian cylinder. At a distance of r, you are finding electric field intensity. At a distance r, this is where you find the electric field. How much is it? Lambda by 2 pi epsilon 0 r. But for calculations, for numericals, you better use this. What have I done here? I multiply this with 2. For compensating, I multiply this with 2 as well. Why did I do this? Now you take 1 by 4 pi epsilon 0 together as 9 into 10 raised to 9. 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. So this is equation number 1. Equation number 2, field due to, so this is field due to, I'll write them one by one, okay? Field due to line of charges. You have to write this down, okay? Write as I do. First point, due to linear charge distribution. Linear charge distribution. Charge distribution. This is linear charge distribution, okay? And right here at a distance r, the field is lambda over 2 pi epsilon 0 r, okay? Or you can multiply with 2 lambda over 4 pi epsilon 0 r. That is first point. Second point, field due to a thick sheet. Field due to a thin sheet of charge. Thin sheet of charge. This is thin sheet. Thin sheet means like the paper of your notebook, like a paper from your notebook, okay? I take a paper and I give charges to it. As you can see, this is surface charge distribution for which the field is sigma by 2 epsilon 0. There is a spherical conductor as well, but I'll come back and do that later. There won't be too many numericals based on that, but these are important questions. I'm repeating one more time. First one is linear charge distribution. It's on a straight line. It's on a straight line. You've been asked to find the electric field at a distance r. What is the equation? Lambda by 2 pi epsilon 0 r, where lambda is equal to q by L, is linear charge density. If you remember, charge by length. We wrote it in the beginning today. Lambda is q by L. Here, due to a thin sheet of charge, if you remember, you draw Gaussian cylinders here to either side and then you find the electric field. Don't worry, we'll do the derivations later. Electric field due to a thin sheet is sigma by 2 epsilon 0, where sigma is total charge by total surface area. It is surface charge distribution. Surface charge distribution. Did you understand these? Question number, section C, advanced level questions. Question number 9. These are based on applications of Gauss's theorem. Question number 9. A simple pendulum whose bob has a mass m and charge q is held at an angle theta from a charged thin sheet. Okay? A simple pendulum. You know what simple pendulum is, right? Whose bob has a mass m and charge q is held at an angle theta from a thin sheet. So this is a thin sheet. Thin sheet, okay? I'm drawing a thin sheet here. You can draw the figure with me, right? This is a thin sheet, okay? Thin sheet is full of charges, positive charges, okay? Thin sheet is very thin. This is a thin sheet, okay? And I'm keeping the thin sheet like this, not like this. I'm keeping the thin sheet like this. I'm seeing the side. I'm seeing the side here, okay? Right. Thin sheet is kept like this. And a simple pendulum is making an angle theta. Simple pendulum is making an angle theta. So this must be positive. Why? The bob must be positive. Why? Then only this positive will repel the positive to the right. It can stay like this. Okay? Read the question again. A simple pendulum whose bob has a mass m and charge q. The bob has a mass m, charge q is held at an angle theta. It is held at an angle theta like this from a charged thin sheet. This is a charged thin sheet. So it's making an angle of theta. And then what? Show that surface charge density is directly proportional to tan theta. Show that surface charge density is directly proportional to tan theta. This is what we are required to prove. Show that the surface charge density of the sheet is directly proportional to tan theta. Let us do this. So pendulum is making an angle like this. Usually if it is held like this. But since this is plus and this is plus, it is making an angle like this because there is repulsion. I'm going to mark the forces. See the forces now? One force is weight of the pendulum. Everybody like me, like you, like this pen, everybody has a weight in the downward direction. Even the bob has a weight in the downward direction. Earth is pulling it down. Mg is the weight. Then what? Electrostatic force to the right. Electrostatic force. Somebody is pushing it to the right. Why? How do we know if it is pushed to the right? It is making an angle. Obviously, somebody must be pushing. Who is pushing? This plus is repelling plus to the right. Electrostatic force is QE. We learned this already. And then what else? There is one more force. That is called tension. Have you heard about tension? If a wire is slack, a wire is suspended from the roof. The wire is slack. Slack means loose. The wire is loose. There is no tension. But if the wire is stretched by pulling it or keeping a weight suspended on it, the wire is under a tension. Okay. You have a wire or a string suspended from the roof. The wire is slack. The wire is loose. There is no tension. But when the wire is pulled, either pulled or a weight is suspended on it, the wire is under a tension. How do you mark tension? From the body outwards along the string. From the body outwards along the string. How is tension marked? From the body outwards along the string. Outwards along the string. So I have marked the tension. Let me repeat. What are the forces on the bob now? One force is the weight exerted by Earth, mg. That is in the downward direction because Earth is pulling the body in the downward direction. Then there is electrostatic force to the right. This plus is repelling plus to the right. That is QE. And there is tension on this wire. Tension is what? From the body outwards along the string. Then tension may be resolved into two components. Any force may be resolved into two components. This angle and this angle are alternate angles, right? Because this line and this line are parallel. These lines are parallel. This one cuts both. These are called alternate angles. They are equal. If this is theta, this is theta. So this must be what then? T cos theta. The component close to theta is T cos theta. The component away from theta is T sin theta. T sin theta. Right. I'm repeating one more time. This angle is theta would mean that this angle is also theta. Why? Because this line and this line are parallel. There is a line that cuts both. So this angle and this angle are alternate angles. If this is theta, this is theta. The component close to theta is cos component, T cos theta. The component away is sin component. Now let us write the condition for equilibrium. Force to the left, T sin theta is equal to force to the right, QE. I have done this once. Force to the left and force to the right are to be equal. Then that is when we call it, the body is said to be in equilibrium. Similar way, force in the upward direction, T cos theta, should be equal to force in the downward direction. We know that the system is in equilibrium. The bob is staying like this would mean that the system is in equilibrium. Force to the right is equal to force to the left. They will cancel each other. Similar way, force in the upward direction, same as force in the downward direction. Force to the right and left. What is that? Force to the right and left. Force to the left is T sin theta. Force to the right is QE. Force in the upward direction is T cos theta. Force in the downward direction is mg. So this is equation number 1, equation number 2, and equation number 1 by equation number 2 implies what? T and T are cut. Sin theta by cos theta is tan theta. Tan theta is equal to QE by mg. Tan theta is equal to Q into E by mg. Sin by cos is tan. What is E? This is a thin sheet. Thin sheet's electric field is what? Sigma by 2 epsilon 0 by mg. Q is a constant, 2 is a constant, epsilon 0 is a constant, m is a constant, g is a constant. So all of them are taken together. If you remove that, you can put the proportionality. Sigma is proportional to tan theta. That is exactly the thing to be proved here. I'm repeating this part here one more time. For equilibrium, what is the condition for equilibrium? All the forces must balance each other. Force to the left should be equal to force to the right. T sin theta is equal to QE. T sin theta equal to QE. Force in the upward direction must be equal to force in the downward direction. T cos theta is equal to mg. This is equation 1, equation 2. Then divide them, you get T and T are cut. Sin by cos is tan. Tan theta equal to QE by mg. That is tan theta equal to Q into, what is E? Electric field due to a thin sheet. This is a thin sheet, no? We wrote it earlier, that is sigma by 2 epsilon 0 by mg. Here, Q is a constant, 2 is a constant, epsilon 0 is constant, M is constant, G is constant. All of them can be taken as a single constant. How do you remove that constant? By putting a proportionality. Sigma alone is there, proportional to tan theta. Did you understand this? Question number 10 is again an important one. An infinitely long positively charged wire has a linear charge density lambda. An electron is revolving around the wire as its center with a constant velocity in a circular plane perpendicular to the wire. Read it again. An infinitely long positively charged wire. Infinitely long positively charged wire. This is infinitely long positively charged wire. Okay. Infinitely long wire has a linear charge density lambda coulomb per meter. Okay. Lambda coulomb per meter. Infinitely long wire has lambda coulomb per meter. An electron is revolving around the wire. Electron is revolving around the wire. This is an electron. Okay. An electron is revolving. A center with a constant velocity in a circular plane perpendicular to the wire. In a circular plane perpendicular to the wire. Deduce the expression for its kinetic energy. Right. Whenever you hear the term circular motion, I have told you before, even the last paper had one question on this. Whenever there is a circular motion, there is a force called centripetal force. Centripetal force is to the center of the circle. Centripetal force. What is centripetal force? mv square by r. Who gives a centripetal force here? Electrostatic force between them. Electrostatic force is Q times C. Okay, I'm repeating one more time. What is happening here? We have a linear charge distribution, a line of charges. And then what? Electron is revolving around it. An electron is revolving around it. Whenever you hear the term electron as revolution, circular motion, this should come to your mind. Centripetal force is there. Centripetal force means to force to the center. It is provided by what? Electrostatic force here. Centripetal force is mv square by r. Electrostatic force. So let us put it. mv square by r is equal to, what is the charge? Charge of electron is E. What is electric field intensity? If you remember, I told you, electric field intensity due to a line of charges is lambda by 2 pi epsilon 0 r. I can cut this r and r. What do we get? mv square is equal to E lambda by 2 pi epsilon 0. What I want is kinetic energy. Kinetic energy is what? Half mv square. Right, this is mv square. I have to multiply with half. So half into E lambda by 2 pi epsilon 0. So E lambda by 4 pi epsilon 0. That will be the equation for kinetic energy. They are asking you to find the kinetic energy. Kinetic energy. Okay. Kinetic energy. And then what? The question, I'm repeating the question one more time. We have a linear charge distribution, line of charges like this. This is a line of charges. And then an electron is revolving around it. Electron is revolving. Revolving means it is circular motion. So centripetal force is anyway involved, right? Centripetal force is involved. What is centripetal force? mv square by r. mv square by r. mv square by r is equal to Q times C. Why? Because the centripetal force is provided by electrostatic force. What is electrostatic force? We learned this before. Q times the electrostatic force is QE. What is the charge here? Electron. So it is moletary. What is electric field? Electric field due to line of charges is lambda by 2 pi epsilon 0 r. R gets cut on either side. You get mv square is equal to E lambda by 2 pi epsilon 0. So kinetic energy is calculated how? Kinetic energy is half mv square. That is half into, this is E lambda by 2 epsilon 0. E lambda by 2 pi epsilon 0. So you get E lambda by 2 and 2 is 4 pi epsilon 0. There is a second part of this question. Plot a graph of kinetic energy as a function of charge density lambda. Kinetic energy and lambda. Plot a graph of kinetic energy as a function of lambda. Kinetic energy and lambda are to be drawn. What is the proportionality between kinetic energy and lambda? E is a constant, 4 is constant, pi is constant, epsilon 0 constant. So I would say kinetic energy is proportional to lambda. Kinetic energy is proportional to lambda. So the graph should be a straight line. For direct proportionality, the graph must be a straight line. Look at this. Kinetic energy is equal to E lambda by 4 pi epsilon 0. Plot a graph of kinetic energy as a function of charge density lambda. Kinetic energy as a function of charge density means you have to draw kinetic energy again as lambda. Kinetic energy as a function of, kinetic energy is on y-axis and lambda is on x-axis. Lambda is on x-axis. Kinetic energy as a function of lambda means kinetic energy is on y-axis, lambda is on x-axis. Look at this, they are directly proportional to each other. Kinetic energy is here, lambda is here, they are directly proportional because E constant, 4 constant, pi constant, epsilon 0 constant. So kinetic energy is proportional to lambda. Direct proportionality means the graph should be a straight line. So the graph is a straight line. Did you understand this? Okay, there is one more type of question I have to do. I'll tell you. We have a cube here. See this? We have a cube here. All right. We have a cube. And, you know, I'm keeping a charge at the center of one face. Charge at the center of one face. What is the flux through this cube? I'm repeating the question. We have a cube here. Look at this. A cube like this. This is the cube, okay? This is a cuboid. But anyway, just imagine this to be a cube. And I'm keeping the cube right at the center of one face. There is a charge like this. The ink mark. No, this is a charge. Okay? I'm keeping the charge here. The question is, what is the flux through this cube? It's a previous question. The flux through the cube is to be calculated. I'll tell you. It's an exemplar question. I'll tell you. For such question, you know, I'll need what? I'll need symmetry. Because if I keep the charge here, the flux doesn't go to left alone. The flux can go to the right as well. So for symmetry, I'll need one more cube on the right side, as you can see. One more cube. See this? One more cube on the right side. I'll have one more cube on the right side like this. See this now? Now it is symmetric. Now the charge is symmetric. Where is the charge? The charge is at the center of the distribution. Am I correct? Charge is at the center of the distribution. To the left of the charge, there is one cube. To the right of the charge, there is one cube. Right? And above the charge, there are two half cubes. Below the charge, there are two half cubes. Behind the charge, there are two half cubes. In front of the charge, there are two half cubes. So I should draw a Gaussian surface in such a way that the system is symmetric. Okay, symmetric. That means it should be same if you look at all points. If I look at all, if I look in all directions. Okay, I'm looking on the right side, I have a cube. I'm looking on the right side, I have a cube. Okay, on either side, left and right, same cube. Behind and in front, I have half cube, half cube. Above the point, I have half cubes. Below the point, I have half cubes. Now I have perfect symmetry. The charge is at the center. What is the equation for flux, total flux? It is Q by epsilon 0. This flux is passing through how many cubes? There are two cubes here. So one cube gets how much? Flux through one cube is what? 5 by 2, because both the cubes should get equal amount. Flux should be evenly distributed, right? So that is Q by epsilon 0 by 2. That is Q by 2 epsilon 0. That is first part. I'm repeating one more time. The question is what? We have actually one cube here, but they are asking, and the charge is placed where? At the center of one face. And for symmetry, I'll construct an extra cube. I'll imagine that there is one more cube. That's imaginary. It is Gaussian surface, okay? Now what? The flux is passing through how many cubes? Two cubes are there, right? So it means what? Flux through the whole cube is, system is Q by epsilon 0. 1 by epsilon 0 into Q. 1 by epsilon 0 into Q. This is Gauss theorem. And flux through one cube is then what? Both the cubes equally share. So 5 by 2. Q by epsilon 0 by 2. Q by 2 epsilon 0. This is flux through one cube. And there can be another question. Flux through one surface is what? Flux through one surface. Look at this. I am shading this surface. That surface is that exposed? No. See, that surface is closed. Because if I take this surface, there is one more cube coming over here. I have one more cube coming over here. This surface will be closed. So how many are open now? 1, 2, 3, 4, 5. Or in a cube, there are 6 surfaces, but this is gone. Where is it gone? It is closed. Why? There is one more cube here. Only 5 surfaces are present per cube. So for 2 cubes, how many surfaces? 5 per cube. 5 per cube. 5 plus 5 is 10. For this guy, there are 5 surfaces. This one, there are 5 surfaces. Altogether, there are 10 surfaces. So flux through one surface is what? Q by epsilon 0 by 10. Total flux by 10. Q by 10 epsilon 0. Did you understand this?